If you did a thought experiment and changed our solar system from the solar system that it actually is to an identical solar system, but in the place of every planet, you put the Earth. So the Earth's in the Earth's orbit, the Earth's in Venus's orbit, the Earth's in Mars's orbit, and so forth and so on, Jupiter's orbit, Neptune's orbit, etc. If you put identical objects, and the object I pick is the Earth because we all agree the Earth is a planet, right? And you then categorize them by the astronomer's definition. What you would find is that they would be planets close to the sun. But by the time you get out to Pluto's orbit and beyond, the Earth isn't a planet either, even though it's the same thing. It's the Earth.
Hello, this is Robinson Earhart here with the introduction to Robinson's podcast number 153. And this episode is with Alan Stern, who is a planetary scientist, space program executive, and aerospace consultant. In 2007 and 2008, he was NASA's chief of space and earth science programs, but right now his main gig with NASA is leading its $880 million New Horizons mission, which explored Pluto and its moons before heading farther out into the Kuiper Belt that surrounds the solar system, and it's heading beyond even there. And in this episode, Alan and I begin by discussing whether or not Pluto should be classified as a planet, because there are some astrophysicists out there who don't think it's massive enough or that it doesn't sufficiently affect the rest of the solar system gravitationally. So a recent guest, Konstantin Batygin of Caltech, is one of them. And then we turn to the logistics of flying to Pluto, which is no easy feat. What the New Horizons probe discovered there and on the way, because it made a stop at Jupiter, and then its journey into the Kuiper Belt. Alan's book, Chasing New Horizons, details the story of this groundbreaking mission if you want to get even more juicy details. And now, without any further ado, I hope that you enjoy this conversation as much as I enjoyed having it with Alan. There are so many different areas within physics and astronomy that one can focus. I know because I've had a lot of conversations with physicists and astrophysicists lately, but ranging from the quite small to the quite large, and the very distant to the very close by. And the immediate first question is why your research and career has centered around our solar system in particular. So what is it about understanding and then visiting these nearby worlds that captured your attention over all the competition?
Well, that's a great question. I've very rarely been asked that, but there are two parts to the answer. The first is that we've learned through the exploration of worlds that you really have to see them up close in order to get them right. And it was my estimation, even at the beginning of my career, when I was an undergraduate and then a grad student, that since we were never going to send spacecraft in my lifetime to other stars or to faraway places in the universe, that the solar system was just a better place to spend your time because you had a chance of actually determining if you got it right. And the others, I'm very wedded to exploration, human exploration. And again, because we don't have a technology to go farther than the solar system, that's where I wanted to put my time.
The first thing you said, that we've learned that you need to see the worlds up close to get it right. By that, do you mean that there's only so much we can really get from flyby pictures or spectra for exoplanets or even for Venus? I spoke with Andy Knoll, who was part of the MER missions to Mars recently, and we were talking about all of the immense amount of information you can get from just looking at the soil that you can't from a spectrum.
Well, you certainly can learn a lot from in situ measurements, but one of the great lessons of planetary science is that for every planet that we ever sent a spacecraft to for the first time, we learned that our preconceived notions, what we got from the Earth, didn't come close to really representing the place. We did not anticipate the true Mars. We did not get Venus right and the toxic environment that it is. We did not think that Mercury was going to be basically the core of a planet who had its mantle and crust largely blown off in a giant collision. We didn't get the Galilean satellites right. And I can go all the way out across the solar system, even Pluto. When we were closing in on Pluto with New Horizons, I told my team, there are 40 years of planetary exploration before us and missions to the 8 planets from Mercury to Neptune. And we have all that perspective. Let's see if we can get the last one right in anticipating it from what we learned from all those others combined with the ground-based data. And we completely underestimated Pluto. It really takes having high-resolution images, spectra, and other data products to get this kind of thing right. And you can only do that by going up close with present technology.
And we'll definitely get into Pluto, but one other dimension that you might have hinted at already, one that doesn't have so much to do with science, is that I imagine that there's also just this deep visceral thrill that comes from putting something and looking out of its eyes on a distant world, and that this can't really be matched anymore on Earth, though. I mean, there are some unexplored places like in the bottom of the oceans, but on the other hand, far off exoplanets remain totally outside our reach, like you said. So Pluto, icy moons, asteroids, that's as good as it gets if you want that visceral exploratory thrill of being somewhere new.
Oh, that's absolutely right, Robinson. And even for places as close as the Earth's moon, we've only been to 6 very small places with humans and a handful of others with robots. And of course, the surface area of the moon is like the continent of Africa. We haven't really scratched the surface. There are lots of places to go and explore there too, and we will.
Yeah, and I saw this picture of you, I think at Johns Hopkins in sort of command center when New Horizons finally got to its closest point to Pluto, and the excitement in the room there is just palpable.
Yeah, there's nothing like that feeling of excitement and discovery that you get when you see a place for the first time and you see it in detail. It's like a Christmas present you've been waiting to unwrap for a long time, and then suddenly you open the box to see what's inside.
Mm-hmm. And you've been part of many missions and research projects in the solar system, but I think that given our time constraints and then some of the other subjects that the show has covered, focusing on Pluto and the New Horizons missions is the way to go. But before we get into the details, I recently did an episode with Konstantin Batygin, who I'm sure you know, of Caltech, who works with Mike Brown. And we talked a bit about Pluto and about the new Planet 9, though whether Pluto is still Planet 9 is something we're about to talk about. But so I have that side of the story where Mike and Konstantin don't think Pluto is a planet. But I was wondering how, as someone who knows Pluto probably better than anyone else, feels about its demotion from planetary status, and whether or not the move reflects something like an arbitrary whim or a meaningful and illuminating distinction, as they would have it.
But we only have an hour. Seriously, there are many ways I can answer that question. And I think the most important is to tell you that the whole topic of what a planet is and what isn't a planet is very important to planetary science. Categorization is extremely important in all the sciences, from geology to biology to zoology to atmospheric science to planetary science to astrophysics, and we could go on, because science is ultimately a reductionist enterprise in which we try to take a mass of observations and facts and distill them down into what's really important and to understand what things are and aren't in different bins, if you will. The move, it was made so famous in 2006 by the International Astronomical Union, really a professional society of people who don't work on planets, who study stars and galaxies, was really misguided because their logic was if we allow there to be too many planets in our solar system, school children will have a hard time memorizing all their names. Now, that's about the least scientific proposition I can imagine. It's like saying we're not going to have more than 8 mountains or maybe 8 elements in the periodic table. I remember once being on Ira Flato's Science Friday debating Mike Brown on this topic. He said, Alan, we just can't have more than 8 planets. It's too hard on the school children. And my comeback was, Mike, all right, I guess we're going back to 8 states here in the United States. Which 8 do you pick? It's just ridiculous. We know that there are countless number of stars and asteroids and galaxies, and school children don't have to memorize their names. On the Earth, there, I don't know how many rivers and mountains, but again, no one has to memorize their names. In planetary science, we've undergone this fundamental transformation from when I was first in school and when I was a child, when the only planets known were the ones that are close to the Earth, Mercury out to Pluto. And then we started discovering exoplanets around other stars. We now know thousands. And we started discovering more planets out beyond Pluto. And so the field is really transformed to where now there are too many planets to memorize, but it doesn't matter. Probably all the school children need to know is that there are a lot of planets that come in many varieties. There are a few famous ones that are close to the Earth, and maybe there'll be a few famous ones far away too, where maybe life is discovered as an example, or they're particularly new types of planets. But the rest you can look up in a book. And any scientist that tells you that we need to limit the number of something so that we can keep them all in our head, I would claim is doing bad science.
Mm-hmm. On the one hand, when I was a child, and for a long time, Pluto seemed constitutive of a planet, and it was every bit as much of a planet as Mars or Venus or any of the others. And I was thinking this morning, it was almost like saying, "Oh, you thought the sky was blue? Well, we've changed the way we think about the color spectrum, and it's purple now." And it just doesn't really seem like a useful distinction or change to make. But then on the other hand, one of the things that Constantine was telling me was that when Pluto was declared a planet, we didn't have a good understanding of its mass, and we thought it was much larger than it was until we had better observations, until we knew it had moons and could really determine its mass. At that point, we realized it was far smaller than what we'd thought, and it didn't merit being. It was more of a legacy planet, and it was time it was changed. But did I capture what they say correctly, and is that still unconvincing?
It's completely unconvincing, and I would say, so what? What we care about in planetary science is understanding what is and isn't a planet. And so we establish that not by the basis of where it is, but by what it is. And the best definition of a planet that I know is called the geophysical planet definition. It's very simple. If it's an object in space that's large enough to be rounded by self-gravity, meaning it's very large, no longer, has an irregular shape like an asteroid or a comet, but it's not so massive that it ignites in fusion and becomes a star, then it's a planet. This geophysical planet definition is not only superior for many reasons, and we can talk about that, but it also turns out to be the most widely adopted. And despite the fact that the popular press hasn't realized it, there's a scientist named Phil Metzger, really a brilliant guy. He's a planetary scientist in Florida, who actually just a few years ago in the 2020s, went and did a literature search of all the planetary science papers since this famous decision by astronomers that they were going to limit the number of planets. And what he did was to find which papers use the geophysical planet definition and which papers use the so-called IAU, or astronomer's definition. Here's what he found. This is very powerful. That no papers use the IAU definition. None. Except those that are about the IAU definition. That in thousands of papers by planetary scientists since 2006, across the board, Pluto's referred to as a planet. Titan is referred to as a planet. The Earth's moon is referred to by a planet. All the things that fit in the geophysical planet definition. So in science, we don't generally take votes because voting in democracy is not how science works. Science works by finding out what's right. And this is really an anomaly to have scientists vote, particularly scientists from the wrong field, from astronomy, which is not planetary science, vote on what isn't a planet. It's about equivalent to having a podiatrist come and do brain surgery. Yeah, they're both doctors, but different fields. So what Metzger found is that no planetary scientists are using the geophysical planet definition in the actual literature. And then scientists are voting with no planetary scientists are using the IAU definition. They're all using the geophysical planet definition in the literature, and that they're voting with their feet. I like something called the Star Trek test because it turns out to just work, even though it's not very scientific. We all know about Star Trek. We all know about Star Trek, and we all know that no matter which Star Trek series or movie you like, the starship's going somewhere interesting. And usually at the beginning of an episode or a film, they show up somewhere, and on the bridge of whatever starship it is, there's a big screen display, and they show you where they are. And out in the audience, people instantly know just by looking at whatever's on the viewfinder, is that a planet or a comet or an asteroid or a star or a Klingon spacecraft or what have you. And frankly, that's about all it takes. People recognize planets when they see them. And if Pluto came up on your Star Trek Enterprise or any other Star Trek viewfinder, and you didn't know what it was, the first thing you'd say is, this week, this episode is about being at some weird planet. I think Star Trek test works pretty well, and it gets rid of all the math, but it correctly sorts things. And that's what we want in science, is a system that allows us to put the planet-like things in the planet category and the star or asteroid or comet-like things in those other bins. And the geophysical planet definition does that really well, just like the Star Trek definition. But the astronomer's definition, that's all about calculating what's nearby and what's cleared its zone, miserably fails at that. And no one uses it. No one in the professional community really uses it.
Yeah, this geophysical definition really does seem to capture the gap between asteroid or minor solar system body and sun, as well as our intuitions about what a planet is. The only thing that seems to be missing to me is we think of planets as objects that orbit stars, but I also suppose that if the Earth were ejected from the solar system, for instance, we wouldn't stop thinking of it as a planet.
You're right. And we now know that there are planets between the stars. In fact, the number of planets that orbit without stars may even be larger than the number of planets that do orbit stars. And they don't stop being planets just because they're not orbiting a star. It's not about where something is. It's about what it is. The same thing would apply, for example, in biology. It doesn't matter whether an object we call a cow is in a herd or by itself on a farm or for that matter, on an ocean liner. Wherever you find it, it's a cow. And the same is true for categorization of other species and for lots of other things. And that's the way we look at it primarily for planets. When we find it, we want to know what it is. And if it fits in the planet bin, it doesn't matter what else it's orbiting or if it's orbiting anything at all. Even planets ejected out of our galaxy are still planets. That doesn't change their nature.
Mm-hmm. And well, the last thing I'll ask about this before we move on to talking about the mission itself is you said that the definition is much more useful. So I can understand why the geophysical definition is more intuitive, but why is it more useful for planetary science?
Oh, simply because we need to to categorize what is a planet versus what is other types of objects. And the geophysical planet definition produces a much better, cleaner, understandable, intuitive, and accurate result. I'll give you an example. If you did a thought experiment and changed our solar system from the solar system that it actually is to an identical solar system, but in the place of every planet, you put the Earth. So the Earth's in the Earth's orbit, the Earth's in Venus's orbit, the Earth's in Mars's orbit, and so forth and so on, Jupiter's orbit, Neptune's orbit, etc. If you put identical objects, and the object I pick is the Earth because we all agree the Earth is a planet, right? And you then categorize them by the astronomer's definition. What you would find is that they would be planets close to the sun. But by the time you get out to Pluto's orbit and beyond, the Earth isn't a planet either, even though it's the same thing. It's the Earth, right? Can you imagine the inaccuracy and fallacy of a definition in which you have 10 identical objects that classify two different ways purely because of where you put them? That's the problem.
This makes sense to me. And I think maybe another way of putting this, or a separate point, is that this definition is clearer and more accurate because it captures or determines a class of bodies that have much more salient features in common and features that we intuitively identify with planets than any alternative definition would.
You're right.
Okay.
Can't argue.
Okay, great. So then let's move on to New Horizons. And I think before we talk about Pluto, what was its trajectory to Pluto? Because I read it left the Earth at a whopping 36 or 37,000 miles per hour, which is just absurd.
Yeah, the trajectory to Pluto was basically a beeline to Jupiter to gain even more speed and a gravity assist, and then direct from Jupiter to the position where it would intercept Pluto come the year 2015. And so it's mostly a straight line. A lot of trajectories in the solar system do loop-de-loops as they're gaining energy and doing flybys. We didn't have to do that. It's pretty much just a straight line.
How does the gravity assist work? Why does shooting right past Jupiter increase the speed?
Well, we have learned, we as a society and a technical community have learned to use the gravitational wells of planets and other bodies to change orbits and very efficiently. We can add or subtract energy from orbits by going around one side of a planet or the other. If you go on the trailing side in their orbit, you gain energy. And if you go on the leading side, you actually lose energy. That'll help you drop into orbit, for example, Cassini probe, the Galileo probe, and many other spacecraft have used that. But the reason that it works is that there is a conservation principle in physics called the conservation of angular momentum. And in orbital mechanics, when a spacecraft or a rock or a comet or an asteroid or what have you flies past another body, the two objects exchange angular momentum from their orbits around the sun. And if you do it right, if you have engineers design it, then you can target your spacecraft to gain speed and change direction in the way you want it to. You can pick the target point so that it will send you, in our case, from a certain target point near Jupiter onto Pluto at an even faster speed by robbing a little bit of the orbital angular momentum of Jupiter and giving it to New Horizons at the expense of Jupiter losing a little bit of angular momentum. And you might say, does that mean Jupiter drops a little bit closer to the sun because of it? Yes, it does. But it's not in any significant way because the exchange is in the ratio of the mass of the planet to the mass of the spacecraft. And of course, Jupiter, which weighs 300, I believe, and 18 times the mass of the Earth, has a mass that must be, I'm going to guess, 20 something orders of magnitude bigger than the New Horizons spacecraft. So the spacecraft picked up 5,000 miles an hour by properly designing that trajectory past Jupiter. And Jupiter lost some tiny, tiny, minuscule fraction of a millimeter per second in speed in exchange. And moreover, this happens all the time because every day meteors and boulders and asteroids pass through the Jupiter system and the Saturn system, and for that matter, fly by the Earth. And that angular momentum exchange is taking place naturally all the time.
So you said it picked up about 5,000 miles per hour. What was its max speed then after slingshotting around Jupiter?
I don't think I have that number in my head anymore.
Yeah, that's fine. That's fine. But I mean, it's more than 36,400 miles per hour. And even that speed, imagining it terrestrially, is just totally preposterous. That's like going around the Earth multiple times in an hour.
Oh, yeah. It's like LA to New York in 4 minutes.
Yeah. Yeah. It's absurd.
My favorite, by the way, is that when Apollo astronauts went to the moon at 25,000 miles an hour launch speed, it took 3 days to reach the moon. New Horizons did it in 9 hours.
That's quick. Hopefully we
That's
have that sort of
3 days.
That sort of a technology when we start vacationing there. But one of the interesting things about these missions in the solar system is that very rarely is the satellite or the probe just doing one thing, because we send these up so seldom. They're stopping, or they're making multiple observations along the way, stops along the way. And I understand that New Horizons didn't just slingshot around Jupiter. It also performed some measurements and observations there. So what work was done there on Jupiter, or around Jupiter?
So first, I mean, the simple answer to your question is we performed over 400 different observations of Jupiter, its moons, and its magnetosphere. But let's face it, we're the 8th mission to Jupiter. And so we were doing a lot of more in-depth work that the first mission that was just all discovery, cleaned up on. We had 3 objectives at going to Jupiter. The first was that gravity assist, and to get it right, because if we had gotten it wrong, it would slingshot us somewhere other than Pluto, which would have been disastrous for the purpose of the mission, which was to go to Pluto. Second thing is that Jupiter is the only thing we passed along the way in a decade-long journey, 9.5 years from Florida to Pluto. And so that was our only chance for a real rehearsal flight test where we passed something and we could test all the instruments and the flyby software and everything else that goes with. So that was our second priority, was flight test. And the third priority, because we were the 8th mission, not the first mission, and only a flyby, not an orbiter, was to do science. It turns out we did some really fine science and made some really significant discoveries about some of Jupiter's moons and its magnetospheric environment, and a little bit about its aurora and even its atmosphere. But I would call those small contributions to Jupiter system science compared to some missions like Juno that's there now orbiting every day, or Galileo that was an orbiter, or even the Voyager missions that went to Jupiter expressly for the purpose of studying Jupiter and satellites and spent a lot more time doing it than we did.
Going back to the first thing you said, I imagine that if you get the slingshot just slightly wrong, the scales of these journeys are so massive that it's totally impossible to course correct. If anything,
no, that's not true. I'm sure we got it wrong because we did course corrections along the way from Jupiter to Pluto that take out those errors. But you have to get it right enough that the fuel that you have on board is enough to make those corrections. So the engineers very carefully calculate where we need to be and put us at that exact aim point near Jupiter to within a very tiny tolerance. They can calculate the tolerance. So we know when it's good enough that we'll have the fuel to clean up whatever tolerance errors there were in the flyby or a knowledge of Jupiter's mass or anything else.
Okay, well then getting to Pluto, one of the things that surprised me as I was reading about New Horizons was that it didn't stay there the way that like Juno is. And I was wondering if that was because of the speed. I think I read that it flew past Pluto at upwards of 50,000 miles per hour. Is that just too fast to stop and orbit at that point?
So, no, it's not too fast, even for our current technology, but it's not practical. So, but let me start and say the first stage of exploration of all the planets is to do flybys. They're simpler, they're less expensive, they get the lay of the land, and then you send in a more expensive probe where you understand the basics so you can send the right instruments. So we always start with the less expensive flyby as the first stage. But secondly, we wanted to get to Pluto as quickly as possible. It's very, very far away, 3 billion miles. And the spacecraft traveled at this enormous speed that took it to the moon in 9 hours and did that 24/7 for 9.5 years, nearly 1 million miles a day, 365 days a year for 9.5 years to get to Pluto. And when we got to Pluto, we were moving very fast. And if you tried to come to a stop, you could not do it with the kind of propulsion technology on board New Horizons. Think about it. It took a rocket 225 feet tall to launch New Horizons. It would take a similar sized rocket to bring it to a stop so you could orbit.
No, that makes a lot of sense.
We have other technology it's called electric propulsion that makes that more efficient. And people have now designed follow-up missions to New Horizons with orbiters that have never been built, but we know what to do, how to build them. And it turns out they take about 20 to 25 years to reach Pluto, because if you're going too fast, even that better propulsion technology can't bring you to a stop to get into orbit. So you have to limit your speed so that you can have enough braking to get into orbit. In the case of New Horizons, that wasn't the objective. The objective was to get there and do it as quickly as possible so that we could get the data back as quickly as possible. And so the spacecraft didn't have to survive any longer in space than necessary to keep the cost down. So the whole objective was to do a flyby. And had we tried to do an orbiter, we probably never would have had the project because it was not affordable.
I hadn't realized that there was this Flyby-Then-Probe model to better fine tune the instruments that you send in that next round. But that makes a lot of sense.
Take a look at Wikipedia or anywhere else, a textbook, and you'll find the first mission to every planet and to every other kind of body like comets and asteroids always begins with flybys. There's not a single exception, even the moon.
So then, how close did New Horizons get when it finally arrived at Pluto, and how long did it manage to collect data before it zoomed on?
Okay, so we got about 12,000 kilometers or almost 8,000 miles from Pluto. We could have gone closer, but we determined that was the optimal distance, because if you went too close, things would be blurred as you went by very quickly. It's sort of like think of Top Gun. If you had a supersonic fighter and you were doing not bombing but reconnaissance, say you were flying by a building. If you come too close, the images are going to be blurred. At the same speed, farther away makes for better results. So there's an optimum between being too far away and not having good enough resolution and being too close and getting too much blurry. We figured out that math, and that was the answer, 12,000 kilometers. Different kinds of missions use different kinds of science. It's not just cameras, or even just cameras and spectrometers. Sometimes we take instruments that sniff the atmosphere, so we need to get into it so we can get the compositional samples or what have you. In the case of New Horizons, it was really about mapping, because we didn't have good maps. We didn't have pictures of Pluto that could show us really anything, even the basics, because it's so far away. So we started studying Pluto the first year after we launched from Earth. And we continued to study Pluto even years after we were at Pluto. But all the real important data came when we were close. In the roughly 10 weeks before the flyby, where we could exceed the resolution of the Hubble Space Telescope. And every day it got better and better until closest approach. And then we were receding again. So almost everything that's important that we learned is in those 10 weeks. And most of that is in the few days right at close approach where we were closest.
Yeah, when I saw and read about the 12,000 kilometers, I was very surprised by that. I thought, oh, maybe if you got closer, you would lose speed or something like that, and that would hinder the trip out into the Kuiper Belt and beyond. But no, this makes total sense, especially when you put it in the example of the fighter jet, that this is the optimal distance for the best measurements.
We did a big what's called a trade study, where we traded the kinds of science we could do with the instruments we have, and looked at all the science for all of these 7 instruments on board, and how well they could study not just Pluto, but also its 5 moons. And Dr. Leslie Young ran that study. It took months because we had to model the performance of 7 scientific instruments studying 6 different objects. So that's 42 combinations of things. And then vary those parameters at distance A, B, C, D, E, F, G. What do we get? And some instruments are better at one distance and some are better at a different distance. And we tried to find the optimal. So we created a scoring system in which we could, the camera might do better here, but the spectrometer there, and the other instrument at some other distance. And yet at every distance, each one of them could teach us new things. So we created a numerical scoring system and just racked it up and determined that this 12,500 kilometers gave the best overall result. And then we nailed it. We went exactly where we said we were going to go.
Yeah, I saw that you really pulled through on all the major objectives of the mission. And you mentioned the 3 with Jupiter. What were the main targets for New Horizons on Pluto?
So, for missions where you go back to a planet, you usually have these very detailed questions because you've already been there and you know what to ask. In the case of Pluto, the 3 top objectives that were set by the National Academy of Sciences in the United States were to map Pluto and its moons geologically, to map their surface composition from place to place for Pluto and its moons, and to determine the properties and composition of Pluto's atmosphere. Now, those are very top level objectives. I'll give you an example. When we talk about the atmosphere, we had very detailed objectives about determining composition to a very specific accuracy, about determining the properties of the haze particles and clouds in Pluto's atmosphere, about understanding the temperature structure of the atmosphere, the pressure structure of the atmosphere. Similarly, for the geology, for the mapping, we had resolution requirements, signal to noise requirements, dynamic range requirements, very detailed specifications from which you can design the telescopes, cameras, spectrometers that do all this work. And the spacecraft that has to accommodate them, point them, record its data, and do all this in a very small amount of time so that everything works out while you're going by. And so what the National Academy did was actually give us a very detailed set of specifications. And we and the other teams that proposed, each came up with concepts for how to do that. NASA selected ours as the best. And then we went and built it and flew it.
Great. And so maybe we should talk about these different areas of the mission in turn. And what did you discover about, well, first, do you pronounce the moon's name as Sharon or Karen? I've heard both.
Yeah, there are actually several pronunciations. It comes from a Greek word. It's the name of the big satellite comes from Greek mythology.
Mm-hmm.
And I don't even think I can pronounce it right. I'm not a Greek scholar.
Right.
I think technically the proper pronunciation is something like Charon, but no one says that. And in particular, the reason for that is because the guy that discovered Pluto's large moon, a guy named Jim Christie, went to Greek mythology, and one of the choices, Charon, sounded to him a lot like his wife's name, Sharon. So he asked everybody to pronounce it like an SH in Sharon. And most American English speakers call it Sharon for that reason, to respect his wishes about his wife. I think his wife's name is Charlene, but it's pronounced like an SH. So Sharon, but in other countries, and some people who maybe know a little more about the mythology will say Charon or Karen or something like that. And it kind of doesn't matter. You say tomato, I say tomato. We know what we're talking about.
Yeah. But what I wanted to ask though was maybe we should start with Pluto and Sharon. I like Sharon's geology. I know that there's a lot of talk about these icy moons elsewhere in the solar system, like Enceladus, and whether or not they might be capable of hosting life, things like that. So what were the most interesting discoveries made about Pluto and Sharon's geology?
Wow. I think if you asked different people on the science team, they would tell you different things. I would say the two most important things we learned about Pluto were, number one, that it broke the mold. The usual rule is the smaller the object, the more simple its geology, the less varied. But Pluto turned out to be as complex as Mars, even though it's much smaller, or as complex as the Earth. And secondly, usually as you look at smaller and smaller objects, they tend to be less geologically active after all these eons because they cool off more rapidly. And there are exceptions to the rule. Some of the moons of Jupiter and Saturn are examples because they have ongoing energy sources that have to do with the gravitational tugs of their planet and other satellites that kind of act like when you take a coat hanger and fold it back and forth real quick, how the vertex gets really hot. That kind of tidal force can make small objects active, even though they're very old. But generally, when we find things in the solar system, the smaller they are, the less active they are. A good example is our moon, which itself is bigger than Pluto, but it's hardly geologically active compared to Pluto. Pluto turned out to upend this whole theory that smaller generally means less active, and showed us that an object the size of basically the United States could be as geologically active as the Earth or Mars, even after 4 billion years. And what I like to say is that defied all the textbooks, but I guess Pluto doesn't read textbooks.
So does that, when you say that it's geologically active, that means it has a hot core, there are plate tectonics, volcanic activity, all sorts of things like that?
Well, we don't know if Pluto has a hot core, and we don't know if it has plate tectonics, but we do see tectonic activity. We do see evidence of recent volcanism. We see there's a large glacier on Pluto's surface called Sputnik. It's the size of Texas and Oklahoma combined, and it's geologically born yesterday. So Pluto's creating new terrains all the time on a massive scale that I don't think you'd have found anybody on my science team before the flyby that would have taken a bet with you that we would find that, because it just defied all common wisdom from the exploration of the closer planets.
And then returning to what you said earlier about this, the way that missions unfold, where first you do a flyby, then you send a more dedicated probe. Is this the sort of discovery where when you send the next mission, it will now be equipped with the sorts of detectors to best measure geological activity, for instance?
Exactly. You're exactly right, Robinson. When we go back with an orbiter, we want to probe the interior because we think we found an ocean lies beneath the surface.
Okay.
We want to probe the atmosphere now that we know that it has these haze layers, and we want to probe the volcanoes and the frozen lakes and the other kinds of phenomenology that we saw to better understand them now that we know that they're there. So we can ignore a lot of things that we didn't find, and now we can concentrate on the things that we did find and bring the right kinds of instrumentation to do that.
Yeah, you said there were two most surprising things about Pluto. Was the second these haze layers in the atmosphere you just referred to?
No, the two were the diversity and complexity of its geologic expression and the youth of its surface, the ongoing activity.
Okay, interesting. And then
Both of those completely defied expectations, and they're like meta. They're not like, oh, we were surprised to find a specific thing like a volcano or clouds or what have you, evidence for an ocean. This is when you put all of the range of phenomenology we saw together, it's those two things that are at the top of the list for headline surprises.
Yeah, so they're meta in the sense that they upend a model or theory that goes way beyond just Pluto.
Yes, but they're also meta because you don't learn them from seeing one type of geologic structure or atmospheric property. It's from putting it all together holistically and saying, wow, look at that. There's this range of geologic phenomena that's just unprecedented for a small planet. There's this range of activity on very many different time scales and on different spatial scales that was not predicted.
And were there similarly surprising discoveries made about Charon or other of Pluto's satellites?
Well, yes, for Charon in particular. The small satellites we didn't come as close to, and because they're smaller, we just put less pixels on them, so we don't see them as well. We have their basic shapes, their basic compositions, their basic masses, but we even have a little bit of information on their composition, but we don't see them in as much detail because the main targets were Pluto and the big moon Charon. And realize the big moon is the size of Texas. It's big. But the next biggest moon is like the size of Houston County. It's really tiny by comparison. And then the other moons are even smaller still. So we went after the two main objects in the system and studied those in greater detail.
And so what was exciting about Charon?
Well, I can name a lot of things, but I will tell you it's not as exciting as Pluto in my view, and I think the view of most people on the science team. But we did find really interesting properties. For example, we found evidence of a lot of ammonia ice exposed on the surface, which means that its interior must somehow make or was born with a lot of ammonia, which is not seen commonly at other places in the solar system. That's a puzzle. Secondly, it's got a polar cap, but it's the opposite of every other polar cap, all of which are bright, icy things. This turns out to be a dark, organic residue polar cap, unlike anything else seen anywhere in the solar system. We found the largest canyon system in the solar system across Pluto's equator, I meant to say Charon's equator, caused by the freezing of the water ice in Charon's interior that created extensional stresses that cracked the whole girth of it around the equator. The same way that if you take an ice cube and throw it in a hot pot of tea or coffee, that you'll hear popping and cracking as the ice expands due to being rapidly heated. Something like that happened to Charon, but on a gargantuan scale that just completely dwarfs the Grand Canyon of the Earth.
Wow. Well, the last thing that I really wanted to ask about regarding Pluto and Charon is that you already mentioned this subsurface ocean. And is it something where with Enceladus, for instance, people are thinking that this ocean might once have been or still be a potential home to life? And if so, is that something that future missions will want to be investigating more closely?
Briefly, the answer is yes and yes.
Great.
Very all cool. Of these oceans, these interior oceans that are so common that we didn't expect in the beginning of the space age, but we've learned to appreciate that they're very common, provide warm and nurturing environments where there may be biology, even far from the sun, like Pluto, where you wouldn't expect to have found life because temperatures on the surface are near absolute zero, but down below the surface, it's warm enough to have liquid water. And that might mean, we don't know enough to know, but it might mean that there's evidence, like we see it in Enceladus, of not just liquid water, but salty liquid water with organic compounds in it, and evidence of hydrothermal vents, all of which is the case at Enceladus. Pluto, we don't know enough yet to know if that's the case, but I guarantee when an orbiter goes back, studying the putative ocean and its properties and its potential for astrobiology will be high on the list of objectives.
Very cool. Well, I want to make sure that we have time to talk about future missions, but before we get to that, we still need to finish the story of New Horizons. So I know that after it visited Pluto, it sped off to a Kuiper Belt object, a KBO, known as some string of numbers, and then Arrokoth that it reached in 2019. So maybe what was this object? Why visit it? What did we find? And then where to go from there?
Right. Well, when the National Academy of Sciences that I referred to earlier outlined the objectives and the priority of doing this mission, it was not just to explore Pluto and its moons, but this whole third zone of the solar system called the Kuiper Belt that orbits beyond the giant planets. And the reason is it's a treasure trove for understanding how planets form. It's in the deep freeze, so it's sort of a planetary equivalent to an archaeological dig back into the history of the solar system. And these little objects that are not the size of continents and larger planets, but that are the size of counties, aren't very evolved. And because they're kept in this deep freeze near absolute zero, they're great time capsules that can tell us about the chemistry and the physics that form the seeds of planets. And Arrokoth is one of those seeds. We call it technically a planetesimal, which is like a tiny planetary building block. And we flew right up to it and past it and got data that's just as fine as the data that we got on Pluto and its moons. We've also studied 36 other Kuiper Belt objects along the way, and we're looking to study more and to even have another close flyby if we get lucky and can find something within our fuel reach.
And how far is New Horizons now, and how far is it going to get?
Well, New Horizons now is about 56 times as far away from the sun as the Earth is. That's about it's getting towards twice as far as Pluto.
Oh, wow.
Not quite, but it's getting there, pretty close. And it's on a trajectory that's going so fast, it's leaving the solar system. So it's never going to reach a maximum distance. It's always going to get further and further by about 300 million miles per year. And we expect that the battery, it's a nuclear battery that's on board, has enough power to run New Horizons until roughly the year 2050. So that's 27 years from now. We've been in flight 16 years. We're not even halfway. And the spacecraft will be much, much further out, more than twice as far as it is now. And we'll, unless something breaks, we'll be able to continue to use it, initially to study other Kuiper Belt objects if NASA funds it, and then further out to study other things once we're past the Kuiper Belt. It's really a unique resource. It's the only spacecraft in the Kuiper Belt or even in the sun's heliosphere at those great distances. And it carries great instrumentation that the Voyager mission didn't have because it was invented 30 years before with older technology.
Yeah, you said that it carries great instrumentation, but that's not the only stuff that New Horizons carries. I saw that it flies with a Florida state quarter, United States flag, some of the ashes of the guy who discovered Pluto, and then a number of other things. And I was wondering whether this is required by NASA for publicity purposes, or is it really born of a conviction by you and the other powers that be that it could be recovered by non-human life forms?
Oh, no, we didn't do it for any of those reasons. We just did it because we worked hard and we wanted to put 9 mementos for the 9th planet. And the things you named are some of those 9. We did it with NASA's knowledge, but it wasn't a requirement. Just like we fly an American flag on the spacecraft. We did it to celebrate the work that we'd done and to commemorate the people who worked on it. And we launched it from Florida as a Florida state quarter. It was built in Maryland as a Maryland, a coin there. Clyde Tombaugh discovered the planet and died before we could build New Horizons, but always wanted his ashes flown to Pluto if a mission ever happened. We were able to do that. And then there are some other mementos. As I said, there are 9. And we did them because there's a bit of historical gravitas to a first mission to the farthest planet. And so we wanted to do some cool things in addition to all that science and engineering.
No, that's very cool. And I see how it's symbolic, and it gets back to how we started the conversation, where it's not just about the science. The science is very cool, but it's also a very human thing about exploring and conquering. Yeah, very neat.
Yeah. And it's important, I think, for people to know that we can do things that are larger than life in our own time. We get so much bad news. It's great to see things like New Horizons, but many others in space exploration and in other kinds of science and technology that are just plain larger than life. And they're just cool. We humans did that. And that makes people appreciate the historical significance of our time and our society. And it can also motivate school kids to study hard things like math and science, and then be the future leaders that invent whole new technologies and economies for the future.
Mm-hmm. Well, the last thing I wanted to get to, because I know you've got your hands in lots of projects, what are the current projects you're working on, or the projects you're most excited to see fly in the next few years?
Well, I like working on a lot of things, and I've been fortunate to be involved now, 30 different space missions, mostly NASA, but also European Space Agency and some commercial private missions. I'm very excited about the Lucy mission, which is a NASA mission that we launched in 2016. Excuse me. We launched it in 2021 to study a new class of asteroid called the Trojan asteroids of Jupiter. It's very important to understanding the origin of our solar system. I'm really excited about Europa Clipper that I'm playing a small role in, which is a mission to be launched next year in late 2024 to Jupiter to study the ocean inside of Europa, Jupiter's planet-sized moon. And I'm also very excited about using the new commercial spacecraft to do research. I'll be flying on Virgin Galactic on a suborbital pair of missions in the near future. I'm really excited about that. And I'm excited about the prospect to do even bigger things in the commercial space industry with rockets and balloons and orbital spacecraft. And I hope to fly in space more than just those 2 times.
So I'd like to ask, though, what is so important about the Trojan asteroids? Is it similar to Arrokoth in that it might tell us something about the early solar system?
Yeah, exactly. So the Trojan asteroids are called Trojans because they orbit at these little gravitational pockets that are ahead of and behind Jupiter on its orbit. And they're basically traps for material, most of which formed at the beginning of the solar system. And so, because Jupiter is very much closer to the sun than the Kuiper Belt, when it formed, it trapped a lot of material from that formation zone in these Trojan regions. And the Lucy mission is going to be the first mission to study these Trojan asteroids that represent these ancient samples, not of what happened in planet formation way out by Pluto in the Kuiper Belt, but much closer to home, where Jupiter orbits. And no spacecraft has ever been to the Trojans yet. And Lucy is going to study almost 10 of them, counting some moons of asteroids, beginning in 2026, 2027, 2028, and extending into the early 2030s at least, if things go as planned. So it's another kind of origins mission, a little bit like New Horizons, but closer to home.
Very cool. And then the last thing is, what are you most curious to find through Clipper on Europa?
I'm very interested to know if Europa's ocean has as much astrobiological potential as the ocean at Enceladus, because it's closer to the Earth. It's more accessible to us. Now, it's in a more difficult radiation environment because it orbits Jupiter. That doesn't matter to the astrobiology because the ocean is shielded by all that rock and ice overhead in the crust of Europa. But it does make it harder the spacecraft have to be hardened so their electronics can withstand that radiation while it's making the studies. But still, finding a astrobiologically interesting ocean around the corner instead of far down the block at Saturn, there's a Jupiter instead of Saturn, will be a big advance. And probably following Europa Clipper, the next thing to do is to put landers down or even to burrow into that ocean. But first, we got to get the lay of the land. We got the orbiters to do the survey to tell us where to land, where we can have access to that ocean.
And I know this is an entire conversation in itself, but to say that an ocean has astrobiological potential, does that mean that one has a heat source and then the components for organic chemistry?
Well, what the astrobiologists, and I'm not an astrobiologist, so I'm just repeating what astrobiologists write down, which is the three key ingredients for potential evolution of life are liquid water, check mark at Europa, the chemical elements that are necessary to make life, that's carbon, hydrogen, oxygen, nitrogen, and a couple of other minor constituents, and then a source of energy to drive the development of biology. And we need to know if the second, third thing are part of the Europa system. We already know that at Enceladus, that's the case. But it'd be great to have an ocean that's closer than Enceladus, and also to be able to compare.
Mm-hmm. Well, Alan, this was awesome. It was compact and there was a lot going on, just like Pluto. So thanks so much for talking with me.
Robinson, it was fun, and thanks for having me on.
Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Earhart.